Hey guys, how's it going? In this video, I'm going to walk through this Leetcode 133 clone graph. This is a medium problem and was asked by Facebook for 24 times in the past 6 months. Let's dive in. So we are given a reference of a node in a connected undirected graph. We need to return a deep copy of the given graph. And each of the nodes in the graph contains each value and also a list of each neighbors. So it has two components. One is the value. Another one is always connected neighbors. Okay. Also, this is some test case format. I'm gonna go with that with you later in an example. In here in this graph diagram, we are given an original graph, so we cannot return the same graph, right? So we have a cross on this arrow. We cannot return the same graph. This looks like a clone. The nodes are new, which are copied, and the graph looks exactly the same, right? The ordering of the neighbors, and also for this one, the nodes were cloned, but the graph is messed up, right? Because it's 1 to 2 to 3 to 4, right? This one's 1 to 3 to 2 to 4, and does not have the same connections, because in this case, it's 1 connects to 2 and 4. In this case, it's 1 connects to 3 and 4, etc. for other nodes. So scrambled. This is no good. So now let's look at the format of the data given. We have a J list, so which represent all the nodes, the neighbors of all the nodes. For example, for the first node, for example, the one in the corner, the top left corner, which connects to 2 and 4, right? So, and this is the representation of that node, right? 2 and 4. Second node connected to 1 and 3, so 1 and 3. Okay. The third node connects to 2 and 4, right? 2 and 4. Okay. And the last node, which is the fourth one, connects to 1 and 3 and 1 and 3. Okay. And the output looks identical because we have to clone this original given graph. Okay. And also there's one edge case where if the input contains only one empty list, the graph contains only the one node with the value of 1. It does not have any neighbors. Also, with another edge case is empty, output should be empty as well. Very trivial example. 1 connects to 2, 2 connects to 1, right? So yeah, so that's all the 4 examples given. Some constraint, number of nodes between 0 to 100 inclusive, value between 1 and 100 inclusive. Also, the value will be unique, okay? There are no repeated edges and no self-looping in the graph. The graph is connected and all the nodes can be visited starting from the given node. Okay, so this is not too bad of a problem. I'm gonna dive straight into the code. I think it's easier to show you how can we implement it with using a breadth first search, a depth first search DFS to this problem. So as you can see, the code looks pretty clean actually. It's not too bad. Let me walk through with you. So now the first step is to cover an edge case. If the node is a none, just directly return a none and no need to do the rest. And now we have the dictionary. Okay, and this dictionary, the key being the old node, the value being the new node. Okay, so this is more or less like dynamic programming. This is like a cache to save all the node that we have copied along the way. Now we have a function. I call it clone. This is a depth first search function, which we will call it recursively. And it takes in an old node, and we return a copy of the given old node. Okay. If we have already worked on this old node, that means if the old node is already in this dictionary, remember the key being, this dictionary, the key being the old node, the value being the copy of that node. Okay, so we can directly do a lookup if we already worked on that node before. We just do a direct lookup. And if we cannot find that node in the dictionary, we're going to do the following. We make a copy of the node for the value. So after we have done the value, we're going to work on the neighbors, right? And before we work on the neighbors, we have to write it to this dictionary, right? So the key being the old node, value being the new copy, the brand new copy we just created. Okay, for all the neighbors, basically this is the old neighbors, right? In this old nodes neighbors list for each one of the neighbors, and then we gonna copy all of these neighbors by recursively calling this function clone at the old neighbors and append. So what it's going to return is a copy of these old neighbors. So I'm going to call it new neighbors. Okay, and then we append this neighbors list, and this list belongs to this new copy. And because we have only two components, right? One is the value, another one is the neighbors. Value, we worked on the value over here. The neighbors, we work on neighbors in this for loop. After we work on these two components, we are done. So we can directly return the brand new copy. Right. So the last thing we have to do is just call this function, and then we just return one of the brand new node in the new clone graph. Submit that, and it works. Looks pretty efficient as well. So for time complexity, it's going to be big O of a number of nodes. For space complexity, it's going to be the same. And if you want to be precise, it's going to be big O of a number of edges and also the vertices for the time complexity. And this is so much in my solution. I hope you find this helpful. If it is, please like and subscribe. Thanks so much for watching. See you next one.